All right, let's just get right into it. Pi.
Mm.
We all learned it in school, right? That number, roughly, 3.14159.
Yeah, the ratio. Circumference over diameter for a circle.
Exactly. And it feels like one of those things that's just, fixed, like totally immutable.
Absolutely. Set in stone.
Yeah, I mean, one of the sources we looked at even flat out says pi is 3.1415, and there is nothing we can do about it.
That really captures how it feels, doesn't it? Like
Yeah.
a universal truth.
It totally does. But here's the kicker, and what our source is really big into. What if that number, that 3.14, is only what you get in a specific kind of space, using a specific way to measure?
Ah, so you're asking if that geometric ratio c divided by 2r could actually be different, depending on the rules.
Precisely. That's the deep dive today. We're exploring these other mathematical worlds where the ratio of a circle's circumference to its diameter isn't 3.14.
And we're looking at sources that explain why, how changing the definition of distance or even the shape of space itself affects this number.
Yeah, our mission is to really unpack that, to see how this geometric pi value is actually a reflection of the geometry you're working in.
Not some universal geometric constant that applies everywhere no matter what.
Okay, so to really get this, we got to start with the familiar stuff. Our home base, Euclidean geometry.
Right, the baseline. When we say pi is c over d or c over 2r, and we get that 3.14159 number,
Yeah.
we're automatically assuming we're in that classical Euclidean world.
Which means basically a flat plane, like a piece of paper.
Exactly. A flat 2D space where the shortest distance between 2 points is just a straight line, as the crow flies.
And that's like the foundation for how we intuitively think about circles and distance and all that.
It is, and it's why that quote feels so right. Pi is 3.1415, and there is nothing we can do about it within those specific Euclidean rules.
Okay. But what happens if we start messing with those rules? What if we change how we even measure distance, even if we're still on a flat plane?
Ah, okay, now it gets really interesting. See, a circle isn't fundamentally defined by looking round.
Right. It's about distance.
It's just the set of all points that are the exact same distance from a center point. So if you change your rule for measuring distance,
You change what the circle looks like and its measurements.
precisely, you change its shape, its circumference, and that C2R ratio.
The sources talk about this family of distance measures, the L sub norms.
Yes, the L subspaces. Think of it like a formula where you can plug in different numbers for p, and each p gives you a different way to calculate distance on that flat plane.
And different pi values give different results for this geometric pi.
Dramatically different results sometimes.
Okay, so walk us through an example. What about when p equals 1?
Right, P1. This gives you the L subs 1 sub, or taxicab distance. The formula simplifies sum. Distance is just the difference in x-coordinates plus the difference in y-coordinates, like the absolute values.
Taxicab, why is it called that?
Imagine driving in Manhattan on a strict grid. You can only go east, west, or north, south. You can't cut diagonally. The taxicab distance is the total blocks you travel.
Gotcha, okay. So if you draw a circle using that distance rule, all points are away from the center. What shape is it? It's not round, is it?
Not at all. The sources show it's actually a square, but rotated 45 degrees, like a diamond shape.
A diamond? Okay.
Yeah. Think about a center at 0, 0. The points are 0, 0, 0, and 0, 0
Mhm.
are all distance away using this rule. R0 plus 0, 0 is 0, 0, 0 plus R0, 0, and so on.
Okay, I see that. So what's the circumference then? Measured the same way.
Exactly. Measured using the taxicab distance. The distance from, say, R0 to 0R is R0 plus 0R, which is R plus R equals 2R.
Right.
And since there are 4 of those sides on the diamond,
So the total circumference is 4 times 2r, which is 8r.
Yep.
8r. So wait, if the circumference c is 8r and the radius is r, then c divided by 2r is 8r divided by 2r, which equals 4. 4. So in taxicab geometry, this geometric pi is 4.
that's right, pi is 4 in that world, directly because we changed the distance rule.
Wow. Okay, that's a big shift from 3.14.
It really highlights how fundamental the distance metric is.
All right, so that's P1. Let's go back to familiar ground. What about P2 in this L sub family?
Ah, P2.
Yeah.
That's the L sub 2 subnorm. The formula becomes the square root of difference in x squared plus difference in y squared.
Which is just Pythagorean theorem.
Exactly. That's our standard Euclidean distance.
And the circle is round, and C2R is approximately 3.14159, our baseline pi.
That's the one. Now, what happens if we let p get really, really big, like approach infinity?
Oh, okay, what happens then?
That gives you the L sub infinity subnorm, also called the Chebyshev distance. Here, the distance is just the maximum of the difference in x. and the difference in y, whichever is bigger.
Maximum. Okay, so what kind of circle does that make?
It makes a square again, but this time it's a square aligned perfectly with the x and y axis.
Huh. So P1 is a diamond, rotated square. P infinity is an aligned square.
Yep. And for this L sub infinity subsquare circle, if the radius is r, the side length is 2r. The perimeter, measured using this Chebyshev metric, again leads to the ratio C to R being 8R, 2R.
Which is 4 again?
4 again. So geometric pi is 4 for p equals 1, taxicab. And as p approaches infinity, Chebyshev.
So it goes from 4 down to about 3.14 at p equal 2 and then back up towards 4.
Exactly. The sources show this transition beautifully. The shape morphs from diamond, gets rounder, hits perfect roundness at P2, then starts squaring off towards the axis-aligned square as P increases.
And the C2R value follows that same path. 4 down to pi, then back up towards 4.
And interestingly, that means the Euclidean value, our familiar pi, is actually the minimum possible value for C2R you can get within this whole L subfamily on a flat plane.
That's fascinating. Okay, so just changing the ruler changes the result, even on a flat surface.
It absolutely does. The choice of metric dictates the geometric pi.
All right, so that's one way. Change the distance rule. What about the other way the course has mentioned? Changing the space itself, making it curved.
Right. Now we leave the flat plane behind and think about geometry on curved surfaces. And here things get even wilder because the ratio C to R generally deviates from Euclidean pi again. And crucially, unlike the L subspaces, where the ratio is fixed for a given p, in curved spaces, the value of C to R can actually change depending on how big the circle is that you draw on the surface.
Whoa, okay, so it's not even constant within the same curved space.
Not necessarily, no.
Yeah.
Let's take positive curvature first. The classic example is the surface of a sphere like the Earth, basically.
Okay, like drawing circles on a globe, and distance is measured along the curve.
Yeah, the shortest path along the surface. It's called the geodesic distance. And the key finding here is that on a positively curved surface, C to R is generally less than Euclidean pi.
Less than 3.14. Why?
Think about it. If you draw a tiny circle on the Earth's surface, it looks almost flat, right?
Yeah, locally flat.
So the C to R ratio for a tiny circle is going to be really close to 3.14159. But imagine drawing a much bigger circle, like one source suggests. Center it at the North Pole. Now measure the radius r along the surface down to the equator. Let's use their example numbers. Say the radius is 6,000 kilometers. The circumference of that circle is the entire equator itself. Let's say that's 24,000 kilometers.
Right.
So C is 24,000 kilometers. The radius r is 6,000 kilometers. What's C to R?
24,000 divided by 2 times 6,000. So 24,000 divided by 12,000. That's 2.
Exactly. For that specific large circle on the sphere, the geometric pi value is 2, much less than 3.14.
Wow. And what if you go even bigger? Radius from North Pole all the way to the South Pole. That's like 12,000 kilometer radius in this example.
Well, what's the circle you trace out at the South Pole with that radius?
Just the pole itself, a single point.
Right. A point has a circumference of 0.
So C is 0. C2R is 0. 12,000, it's 0.
0. So on a sphere, the geometric pi isn't constant. It can be close to 3.14 for small circles, but it decreases as the circle gets bigger, even going down to 2 or 0.
So the positive curvature somehow like pulls the circumference in, makes it smaller than you'd expect for that radius?
That's a great way to put it. The space curves inward on itself. Mathematically, the formula involves sine C equals 2 r sin RR. That sin RR divided by RR factor is always less than 1 when R is positive, pulling the C to R ratio below.
Okay, got it. Positive curves means C2R is less than pi. So what about negative curvature?
That's hyperbolic geometry. Think saddle shapes or Pringles chips locally. The space curves away from itself.
Okay, and what happens to C2R there?
It's the opposite. In negatively curved spaces, C2R is generally greater than Euclidean pi.
So the space kind of stretches the circumference out relative to the radius.
Exactly. It opens up more than flat space. The formula involves hyperbolic sine, sin. C2R involves a factor of sin r divided by ER, which is always greater than 1 for positive r.
So C2R is pushed above 3.14. Does it also depend on the circle size?
Yes. And in hyperbolic space, as the radius r gets bigger, the C2R ratio actually increases, getting further and further above pi. It doesn't come back down like on a sphere.
Okay, so let's recap the curvature part. Flat space, 0 curvature, C2R is pi. Positive curvature, like a skier, C2R is less than pi and depends on radius. Negative curvature, hyperbolic, C2R is greater than pi, and also depends on radius.
You got it. The ratio C2R acts like a detector for the curvature of the space.
This is wild. We've changed the ruler on a flat plane. We've curved the plane. What else is there? The sources mentioned something really out there. P-adic numbers.
Yes. Now we're jumping into a truly different kind of mathematical structure. P-adic numbers, Q sub sub, are built on a totally different idea of distance.
How different?
It's based on divisibility by a prime number p. Two numbers are considered close if their difference is divisible by a high power of p. It's completely non-intuitive compared to distance on a number line.
Wait, divisible by a high power means closer?
Yep. So like in the three adics, 1 and 10 are closer than 1 and 4, because 10 minus 1 is 9, which is 3 squared, but 4 minus 1 is 3, which is just 3 to the first power. Higher power of 3 and the difference means closer.
Okay, my brain hurts a little. That's weird.
It leads to profoundly weird geometry. It satisfies something called the ultrametric inequality or strong triangle inequality.
What does that do to things like circles?
Oh, it makes them behave incredibly strangely.
Oh.
P-adic balls or circles have bizarre properties. Like every point inside a ball is also a center of that same ball.
Every point is a center.
How? Yeah, and any two balls are either completely separate or one is entirely inside the other. No partial overlaps like Venn diagrams. They're also both open and closed sets at the same time, clopen. It's a geometry that defies easy visualization.
Okay, so in this ultrametric p-adic space, what about pi? What's the C2R ratio? One source asks, so what's the pi then?
And the answer is complicated. Or maybe not what you'd expect. The crucial point the sources make is that the real number pi, the 3.14159, it simply doesn't exist as an element within any p-adic field Q sub sub.
Pi isn't even in the p-adic numbers.
No. It's described as an Archimedean concept tied to the real number line. P-adic systems are non-Archimedean. They're fundamentally incompatible in that sense. There's no natural way to just represent pi within the p-adic framework.
So you can't calculate C2R and get pi because pi isn't there to be gotten.
Pretty much. And the concepts of circumference and diameter themselves don't really translate in a way that gives a meaningful constant ratio analogous to geometric pi. The ultrametric distance just behaves too differently. While there are related advanced concepts like p-adic periods, they aren't the simple geometric C2R ratio we've been tracking.
Yeah.
So for p-adic spaces, the answer to what's the geometric pi is basically that the question doesn't make sense in the same way the concept doesn't carry over directly.
Wow. Okay. So let's try and pull this all together. We started with pi is 3.14, and that's that.
Right. The immovable constant.
But we found that if you're talking about the geometric measurement C2R, well, it can be 4, like in taxicab or Chebyshev geometry.
Or it can be less than 3.14, like on a sphere.
Or greater than 3.14 in hyperbolic space.
And in some really different mathematical spaces, like p-adic numbers, the whole C2R concept doesn't even really map onto pi in a straightforward geometric way.
So the big takeaway here is not that the abstract number, the mathematical constant, is changing.
No, that constant is still defined in its own way, often through analysis or infinite series.
But the result you get when you physically or geometrically measure a circle's circumference and divide by twice its radius, that result depends entirely on the rules of the game.
Exactly. It depends on how you define distance or what the curvature of your space is.
That C2R measurement, it's like a signature. It tells you something fundamental about the geometry you're in.
If that ratio isn't pi, it's a flag saying, warning, you're not in Kansas anymore. Or rather, you are not in standard Euclidean geometry.
And this matters, right? Because our intuition is so locked into that Euclidean world.
Completely. We think in straight lines and flat planes. Exploring these other geometries, the ones our sources lay out, it just shows how flexible and powerful mathematics is. It forces us to question those basic assumptions.
It's not just a party trick, as one source kind of joked. It's about understanding that even things that seem rock solid, like geometric pi, are actually built on specific foundations. Change the foundations.
And the building looks different.
Yeah.
Euclidean geometry with its C2R pi is special, yes. It's the minimum in the L subsub family. It's zero curvature. But it's one case among many possibilities.
So we've seen the geometric ratio change based on the metric, based on curvature, and even become ill-defined in p-adic space. It really makes you wonder.
What else?
Yeah, what other mathematical truths that feel absolute are actually just features of the specific systems we typically use? What happens if we change other fundamental rules?
That's a fantastic question. And it drives mathematical exploration. You know, it's funny, one source note mentions that for practical physics, 42 digits of pi are enough.
Right, for calculating the universe or whatever.
But then I contrast that with mathematicians calculating pi to, what was it, 62.8 trillion digits?
Yeah, which seems absurdly impractical.
But it highlights that difference, right? The practical need versus the pure conceptual drive to understand these numbers and these spaces and all their possible variations. Exploring where pi isn't 3.14 tells us just as much, maybe more, about the nature of space and number itself.